Okay, the formulas you probably used in learning the differential. And to use them, I say check the applicable phrases. I can put boxes here. One box as a basis for understanding differentials, because these formulas could be used as a basis for really understanding differentials. Or they could be used to get your homework done on time, irrespective of understanding. Whether you understand it or not, you got pressure to get your homework in, and it's very understandable that if you don't really get it, you use that formula and you plug numbers into it, and you hope that eventually you can do that well enough to do well on the tests, and maybe you hope to really at some point in the future gain a full understanding. Of course, if you got a really good problem set, that strategy could be a start. Okay, to pass a test, to pass test problems without understanding them, that goes into the whole idea of you can use these formulas without understanding a thing about them and pass many test problems, depending on how you're tested, the level at which your course is taught and tested. At a high level, you're probably not going to get many problems that allow you to do that. Okay. To delude yourself into thinking you understand because you get the right answer, and I don't recommend delusion. If you're going to just use it as an expedient to get your homework done because you need the points and you are really working to understand it, then there's no need for delusion. You just understand that you don't understand it, and you keep working to understand it within the constraints that life and work allow. Because I certainly understand that life and work and other courses, which I guess are part of life or work, depending on how you regard them, you do got to get by, and at some point you're not going to do everything ideally because you just don't have time. So you got to judge where to cut that off, or to represent and embody something you do understand. Okay. Now I'd say if you do understand what we saw in the preceding videos, then you do understand differentials. Whether these formulas really embody that understanding or not, well, hopefully what you understand, and whichever form you saw the formulas in, whichever form you prefer the formulas, hopefully if you didn't completely understand them at that point, you'll be able to combine the intuitive understanding with the formula and really understand what a differential is, so you can use it, so you can pull it out of memory and understand it and see what's going on in situations where you otherwise would not have. In any case, here are the formulas as they are most often presented. Okay, now I used, incidentally, my form was, and I'll write it over here. This is not the form you usually see it in. I use delta y and delta x, not because my notation is all that much better, but to emphasize the fact that these are finite changes in x. There's some confusion when you write a dy or a dx, because generally dy and dx refer to infinitesimal changes, very tiny, changes that actually are thought to approach zero. Okay, and there's a little inconsistency in the notation, and there's no really good solution. There are shortcomings of this notation and there are shortcomings of this notation. Okay, anyhow, the more traditional notation, okay, these all say exactly the same thing that I said before using this notation, where dx represents a finite change in x. Okay? So, and x represents what we're going to think of as an initial or starting point. So if we understand this, then we see that we're simply going to multiply a finite change in x by the derivative in order to get the change in y. And in terms of what we've seen already, it should be very clear to you that that's what we mean by what I'm calling the differential, which is, completely consistent with the definition of the differential. And of course, y prime of x could be written dy dx. Instead of y of x, you could use f of x, very common notation, so that now you have df of x. Now I could have written dy of x up here. I can write this as df of x, same thing, derivative times the change in x. Or just df equals f prime of x times dx. Any of these notations are okay. Some are probably more okay than others in that they're more consistent with the notations you usually see, but they all have the same meaning, and the meaning is simply that. You have a point. Excuse me. What? Not sure where that came from, some pollen or something. Okay, you have a point, x, y of x, or if you prefer x, f of x. Either way, you got a point. And you got a line with slope that we could represent as y prime dy dx, f prime of x, f prime, etc. All these things are just the value of the derivative, the rate of change of the function with respect to x. And then we have a dx here, and a change in y, which I could represent as delta y, or a change dy, or df. Okay? That's it. That's what the differential tells us. Now there's an intuitive level of understanding that I'm going to reinforce here in just a second. The bottom line, an idea that should be very intuitive and should immediately occur to you when you get into a situation where differential approximation is called for. Bottom line is that you multiply your rate of change by the change in x to get your approximate change in y, or if you want to call it f, your approximate change in f. Now there are qualifiers that need to go into that. I would say multiply the rate of change of y with respect to x, or of f with respect to x, by your change in x, and so forth. And the rate of change is evaluated at some initial point x, and your change in x goes from that initial point in the way that we've seen. So all those qualifiers go into it, but there's your bottom line intuitive statement, and you just need to apply this in a common sense manner, and you get good results.